Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. For Hodgkin, this was a revelation. Here was a method that promised to move beyond the flat, lifeless diagrams of the textbook and render the intricate folded shapes of proteins and other biological giants in their full spatial glory. Under Bernal's guidance, she learned the demanding craft, the delicate art of coaxing fragile biological substances into forming ordered crystals, the patience required for hours-long X-ray exposures, and the intellectual rigor needed to interpret the resulting patterns of scattered light. Upon her return to a fellowship at Oxford, Hodgkin sought a challenge that would truly test the limits of this new science. She found it in the cholesterol molecule, the steroid nucleus, the fundamental framework of cholesterol, sex hormones and bile acids, was one of the most significant and fiercely debated structural problems of the era. Leading organic chemists had proposed competing models for its arrangement of fused carbon rings, but their arguments were based on the ambiguous results of chemical degradation. The molecule was too complex, its interconnected rings too stable, for its secrets to be surrendered through conventional chemical interrogation. It was a Gordian knot of carbon atoms, and Hodgkin aimed to slice through it with the penetrating beam of an X-ray. Her chosen compound was cholesterol iodide. The addition of a single, heavy iodine atom to the molecule was a stroke of strategic brilliance, the key to unlocking the entire puzzle. The central difficulty in crystallography, known as the phase problem, is that while the diffraction pattern reveals the intensity of the scattered X-ray waves, it discards their phase information. Without the phases, one cannot simply compute a direct image of the electron density, the very map that reveals the atom's locations. It is akin to hearing the volume of every instrument in an orchestra without knowing when each one played its notes. The result is noise, a symphony. To navigate this, Hodgkin turned to the Patterson function, a mathematical technique developed only a few years earlier. A Patterson map plots the vectors between every pair of atoms in the crystal. For a molecule like cholesterol, composed of dozens of light carbon and oxygen atoms, the map is a bewildering superposition of thousands of small, overlapping peaks, an almost unreadable landscape. Hodgkin's insight was to recognize that the iodine atom, with its massive cloud of 53 electrons, would act as a powerful beacon. The vectors between the heavy iodine atom and its neighbors would produce peaks on the Patterson map of such commanding intensity that they would stand out from the background chatter of the lighter carbon-carbon interactions. The labor involved was monumental, a testament to an era of heroic pre-digital calculation. After coaxing the fragile cholesterol iodide into crystalline form, Hodgkin meticulously recorded hundreds of diffraction spots on photographic film. Then began the immense task of analysis. With slide rules, logarithmic tables, and endless strips of paper for performing Fourier summations, she and her small team computed the Patterson maps by hand. It was a process demanding monastic patience and absolute precision, where a single arithmetic error could send the entire, painstaking reconstruction astray. Slowly, out of the mathematical fog, the beacons appeared. By identifying the strong peaks corresponding to the vectors between iodine atoms in the crystal lattice, she could pin down their precise locations. This gave her a fixed point of reference. From there, she could begin the painstaking process of identifying the fainter, yet still significant, peaks representing the vectors from the known iodine positions to the unknown carbon atoms of the steroid skeleton. It was an act of meticulous triangulation, a form of atomic cartography that allowed her, piece by piece, to build up a picture of the entire molecule. The result, finalized in the early 1940s, was a triumph. Hodgkin produced the first complete, three-dimensional structural determination of a steroid. Her electron density map was unambiguous. It confirmed the hunches of some chemists and refuted the theories of others, settling a long and contentious debate with the quiet authority of physical evidence. The tangled knot was untied, revealing the elegant, non-planar architecture of the fused rings. This achievement resonated far beyond the specific structure of cholesterol. It was a powerful demonstration that X-ray crystallography, in the hands of a master practitioner, was capable of solving the structures of large, complex, and biologically crucial molecules. She had validated a method, and in doing so, had equipped chemistry with a revolutionary new sense. This newfound capacity for seeing the unseen would soon be called upon to address a biological puzzle of even greater urgency, a molecule whose structure held the key to saving millions of lives in a world plunged into war. The world at war accelerated the pace of discovery while simultaneously imposing severe constraints upon it. The miracle of penicillin, a substance exuded by a common mold, promised to revolutionize military medicine, to rob infection of its power over the wounded. Alexander Fleming had observed its effect. Howard Florey and Ernst Chain had demonstrated its therapeutic potential. Yet, converting this laboratory curiosity into a scalable weapon against disease presented a formidable obstacle. The yield from fungal cultures was agonizingly low. The only path to producing the quantities needed to treat millions of soldiers lay in total chemical synthesis, and synthesis demanded a blueprint. One had to know precisely how the atoms of penicillin were arranged in three-dimensional space. This very question had fractured the elite world of organic chemistry. A fierce intellectual battle was being waged between two camps, led by titans of the field. On one side stood Sir Robert Robinson, a commanding figure in British science, who proposed what was known as the thiazolidine oxazolone structure. His model was chemically sound, built upon established principles of molecular stability and reactivity. It was an elegant, logical, and widely accepted hypothesis. On the other side, Ernst Chain, one of penicillin's own pioneers, along with his colleagues, championed a different architecture. Their proposal featured a highly unusual and seemingly unstable arrangement, a four-membered ring known as a beta-lactam, fused to a second five-membered thiazolidine ring. To many chemists, the beta-lactam structure looked precarious, a tense and strained configuration that ought to fly apart. The energy required to hold such a ring together seemed immense, making its existence in a natural product appear deeply improbable. The debate was intense, with the future of a life-saving drug hanging in the balance. Chemical degradation studies, the traditional method for deducing structure, yielded ambiguous and conflicting results, feeding the controversy with more heat than light. Into this scientific maelstrom stepped Dorothy Hodgkin. Her recent success with cholesterol had showcased her profound expertise in coaxing structural secrets from crystalline solids. She was invited to join the transatlantic penicillin project, a massive collaborative effort between British and American scientists. The task assigned to her Oxford laboratory was to provide the definitive answer through the physical method of X-ray crystallography. The challenge was immense, conducted under the privations of wartime Britain. The penicillin molecule itself was delicate and prone to degradation. Obtaining crystals of sufficient quality and size was a painstaking process, requiring immense patience and skill from her collaborator Barbara Lowe. The crystals they managed to grow were minuscule, demanding the utmost precision in handling and analysis. The work began in 1942. The process was a testament to intellectual fortitude and computational grit. Each diffraction spot captured on film represented a piece of the puzzle, a component of the Fourier series that, when summed, would generate a map of electron density within the crystal. Reconstructing this map was the central challenge. In an era preceding modern computers, these summations were performed by hand, a mind-numbing, repetitive task of adding thousands of terms using calculating machines, or, more often, paper strips known as beaver slips and strips. The labor was shared among a small team, working for hours on end in a chilly, unheated room at the Oxford University Museum of Natural History. Hodgkin, battling the chronic pain of her rheumatoid arthritis, guided the entire process with an unwavering focus. The first electron density maps, calculated from the diffraction data of potassium and sodium penicillin salts, were fuzzy and difficult to interpret. The molecule was complex, and the data were incomplete. A breakthrough came with the analysis of rubidium penicillin. The rubidium atom, being much heavier than the carbon, oxygen and nitrogen atoms that form the molecular backbone, scattered X-rays far more intensely. Its powerful signal acted as a beacon, a known point of reference within the crystal lattice. By locating the position of the heavy rubidium atom, Hodgkin could begin to resolve the phases of the other diffraction spots, a critical step in producing a clearer image. This heavy atom method, while known in principle, was applied here with masterful effect to a molecule of significant biological importance. By 1945, after 3 years of relentless effort, the picture emerged from the mathematical fog. The painstakingly calculated electron density map was laid out on stacked glass plates, creating a three-dimensional representation of the molecule. The contours were unequivocal. They traced, with absolute clarity, the strained four-membered beta-lactam ring. There was the square-like structure, fused to the five-membered thiazolidine ring, precisely as Chain's group had hypothesized. The chemically improbable was physically real. Robinson's elegant oxazolone structure was nowhere to be found in the electron landscape. The evidence was visual, direct, and irrefutable. Hodgkin's result was a thunderclap in the world of chemistry. When Sir Robert Robinson was shown the map, he, as a great scientist, immediately and gracefully conceded. The physical evidence overrode all chemical intuition to the contrary. The quiet power of X-ray diffraction had settled one of the most contentious debates in contemporary science. The implications were profound and immediate. The confirmation of the beta-lactam ring was the key that unlocked the secret of penicillin's power. Its strained, four-membered structure is what makes it so chemically reactive, allowing it to bind to and deactivate the enzymes that bacteria use to build their cell walls. The molecule is in essence a perfectly shaped chemical explosive, and its structure explained its potency. This fundamental understanding, provided by Hodgkin's map, became the bedrock for the entire field of beta-lactam antibiotics. It guided the development of countless semi-synthetic penicillins and cephalosporins, drugs that have saved hundreds of millions of lives in the decades since. Her work on penicillin was a landmark achievement, a demonstration of fundamental science, providing a critical answer to a problem of immense human consequence. This triumph over a molecule of such complexity and medical urgency further solidified her method and her reputation, preparing her for a new quest to illuminate an even more intricate biological masterpiece. The triumph over penicillin furnished a powerful new grammar for understanding the language of molecular action, preparing Hodgkin for a new quest to illuminate an even more intricate biological masterpiece. This next chapter in her scientific odyssey would take her to the very edge of what was considered possible, to a molecule whose complexity was so profound that many of her contemporaries believed its secrets were permanently beyond the reach of their science. The target was vitamin B12, the enigmatic anti-pernicious anemia factor. Its discovery had transformed a fatal disease into a manageable condition, yet the molecule itself remained a ghost. Chemists knew it contained a single atom of cobalt, an unusual feature for a biological compound, surrounded by a vast and bewildering scaffold of carbon, hydrogen, nitrogen, oxygen, and phosphorus. Its chemical formula alone, C63H88, Co-N14014P, was a declaration of defiance. With nearly 100 atoms, it dwarfed penicillin, presenting a structural puzzle of a completely different order of magnitude. To solve it would require a decade of relentless effort, a journey that would push the very techniques of X-ray crystallography to their breaking point and forge a crucial alliance with the new world of electronic computation. The challenge of B12 was a challenge of scale and of the unknown. The central cobalt atom, while a tantalizing clue, was embedded within an organic framework of unprecedented intricacy. The problem for the crystallographer is always the phase problem. The X-ray diffraction pattern records the intensity of the scattered waves, but it loses the information about their phase, their relative timing. Without the phase information, one cannot reconstruct an image of the electron density, the very map of the molecule. For smaller molecules, chemists could sometimes make educated guesses. For B12, such guesswork was futile. The molecule was a continent of atoms, and its geography was a complete mystery. Hodgkin recognized that the cobalt atom, being so much heavier than all the others, would scatter X-rays far more powerfully. It could serve as a unique landmark, a heavy beacon in the molecular fog. By analyzing the diffraction pattern with a mathematical technique known as the Patterson function, which maps the vectors between all atoms in the crystal, she could locate the cobalt atoms first. The vectors between the heavy cobalt atoms would produce the strongest signals in the Patterson map. Once the cobalt was placed, it could be used as a reference point to begin the long, arduous process of phasing the thousands of other reflections and slowly, painstakingly revealing the positions of the lighter atoms surrounding it. This heavy atom method was elegant in principle, yet Herculean in practice. The sheer volume of calculations was staggering. Each potential atomic arrangement required the computation of structure factors for thousands of individual X-ray reflections, a process that would then be refined through successive Fourier synthesis to generate the electron density map. For her work on penicillin, Hodgkin and her team had relied on punched card tabulators and their own tireless manual calculations. For B12, this was an impossible proposition. A single three-dimensional Fourier synthesis could take months of human labor, a process so prone to error that its reliability was always in question. The intellectual path forward was clear, but it was blocked by a mountain of arithmetic. The solution to this impasse came from across the Atlantic, through a collaboration with the American crystallographer Kenneth Trueblood at the University of California, Los Angeles. Trueblood had access to one of the world's first powerful digital computers, the Standard's Western Automatic Computer, or SWAC. This transatlantic partnership marked a pivotal moment in the history of science. Hodgkin's team in Oxford would meticulously prepare the crystals, collect the diffraction data, and perform the initial analyses. They would then send the thousands of intensity measurements by airmail to California. There, Trueblood and his colleagues would feed the data into the SWAC, a room-sized behemoth of vacuum tubes and wiring that could perform in a few hours the calculations that would have consumed a human calculator for the better part of a year. The computer would churn through the Fourier summations and the resulting printouts, sheets of numbers representing the electron density at different points in the crystal, would be flown back to Oxford. For Hodgkin, these printouts were dispatches from an invisible world. She would take the sheets of numbers and by hand plot them onto transparent slides, a technique she called boxes. Stacking these slides one on top of the other, she could peer down into a three-dimensional representation of the molecule's structure. Slowly, calculation by calculation, shipment by shipment, the ghost of B12 began to acquire substance. Through the late 1940s and into the mid-1950s, the structure gradually emerged from the numerical haze. The initial maps, guided by the cobalt atom, revealed fragments of the surrounding structure. With each successive refinement, a new piece of the puzzle would click into place. What she and her team eventually uncovered was a molecular architecture of breathtaking beauty and novelty. At the heart of vitamin B12 lay a structure never before seen in nature. It was a macrocyclic ring system, somewhat analogous to the porphyrin rings that cradle iron in hemoglobin or magnesium in chlorophyll, but it was fundamentally different. This new structure, which they named the chorin ring, was less symmetrical, more puckered, and possessed a unique chemical connectivity. It was a magnificent, intricate cage of atoms built around the central cobalt. The final analysis, completed in 1956, revealed the entire glorious molecule, the chorin ring, with its complex side chains, and a nucleotide-like group attached to the cobalt atom, folding back to connect with the ring itself. The complete three-dimensional map was a landmark of chemical science, a testament to a decade of persistence, intellectual insight, and the pioneering use of computational power. It was the definitive solution to one of the most formidable structural problems of its era, an achievement that would be recognized with the highest honors in science, and which solidified the power of crystallography to illuminate the deepest secrets of life. The successful elucidation of the chorin ring system, a monumental achievement, served as a prelude to the ultimate challenge she had pursued for decades, the protein insulin. This quest began in 1934, long before the complexities of penicillin or vitamin B12 had been fully confronted. In that year, a young Dorothy Hodgkin, working alongside J.D. Bernal, obtained the first coherent X-ray diffraction photograph of a crystalline protein. The pattern that emerged from their insulin crystal was rich with information, containing hundreds of distinct reflections. It was a moment of profound revelation. It demonstrated that proteins, these sprawling giants of the cellular world, possessed a definite, ordered, and therefore knowable structure. The image was a promise, a tantalizing glimpse into a new continent of scientific understanding. Yet, the tools to map that continent were still decades away from being forged. The sheer number of atoms, the bewildering complexity of the diffraction data, and the intractable nature of the phase problem for a molecule of such scale placed a direct solution far beyond the reach of 1930s science. The problem of insulin had to be set aside, a sleeping giant in her laboratory notebooks, awaiting a future of greater technical and computational power. Her intervening work on cholesterol, penicillin, and vitamin B12 was the necessary apprenticeship for this final ascent. Each structure she solved was a masterclass in confronting and overcoming escalating levels of complexity. With each project, she and her contemporaries refined the techniques of isomorphous replacement, honed their analytical skills, and pushed the boundaries of what was computationally feasible. The journey through the labyrinth of B12, with its nearly 100 atoms excluding hydrogen, equipped her with the experience and the intellectual fortitude required for the molecular Everest that was insulin. By the 1960s, the scientific landscape had transformed. The development of more powerful X-ray tubes, the invention of automated diffractometers for data collection, and most critically, the arrival of electronic computers capable of performing the millions of calculations required for Fourier synthesis, had finally brought the promise of 1934 within the realm of possibility. The final assault on insulin began in earnest. The project, which had spanned the entirety of her independent research career, now drew together a dedicated international team in her Oxford laboratory. The technical hurdles remained immense. Growing protein crystals of sufficient quality and stability was an art form in itself. The central challenge, the phase problem, required the painstaking preparation of multiple heavy atom derivatives, where atoms like lead or mercury were subtly incorporated into the crystal lattice without disrupting its overall structure. By comparing the diffraction patterns of the native insulin crystal with those of its heavy atom derivatives, her team could begin the arduous process of deducing the phase information for each reflection. The calculations were staggering, a deluge of data that would have consumed lifetimes in the era of mechanical calculators. Fed into the new computers, the numbers slowly began to yield their secrets. In 1969, 35 years after she had first captured its ghostly diffraction pattern, the structure of insulin was solved. The electron density map, contoured and built into a physical model, revealed a molecule of breathtaking elegance and economy. It confirmed Frederick Sanger's Nobel-winning work on its primary sequence, while elevating it into 3 dimensions. The structure showed 2 polypeptide chains, the A chain with 21 amino acids and the B chain with 30, held together by 2 disulfide bridges. These chains were folded into a compact, globular shape, a masterpiece of molecular architecture. The analysis further revealed how 6 of these insulin monomers elegantly assemble around 2 zinc ions to form a stable hexameric complex. This was the storage form of the hormone, the very configuration used by the pancreas to hold insulin in reserve. The solution was a watershed moment for biology. It provided the first detailed view of a protein hormone, offering profound insights into its stability, its mechanism of action, and the structural basis for its vital role in regulating metabolism. The long wait was over. The sleeping giant had awakened and revealed its form. Dorothy Hodgkin's career represents a progressive, systematic conquest of molecular complexity, a journey into the very heart of biological matter. Her path led from the relatively planar architecture of sterols, through the strained and unusual ring of penicillin, to the magnificent, intricate cage of vitamin B12, and culminated in the folded polypeptide chains of a protein. Each molecule presented a greater challenge. Each solution provided a deeper understanding of the chemical principles that govern life. Her enduring contribution, however, is a fundamental transformation in scientific epistemology. She was the principal architect of the bridge connecting the world of abstract chemical inference with the tangible visual reality of molecular biology. Before her work reached its full fruition, the structure of a complex organic molecule was something to be deduced, a conclusion reached at the end of a long chain of chemical reasoning, degradation, and synthesis. It was a brilliant, powerful, yet indirect mode of knowing. Hodgkin's crystallography changed the very nature of the evidence. She made it possible for scientists to see. She translated the faint whispers of diffracted X-rays into the precise 3-dimensional coordinates of atoms in space. She gave the world the blueprints for the essential machinery of life, rendering the invisible architecture of the cell in unambiguous detail. This ability to visualize molecules laid the bedrock for the entire fields of structural biology and rational drug design. It forever altered how we approach questions of biological function, disease, and medicine. Her legacy is written in the very way we now perceive the fabric of our own existence. A shift from reasoning about life's components to witnessing their intricate and beautiful reality.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.